All right, so table O, again, this is in your reference table in terms of the name and the notation and the symbol. Make sure, guys, you're aware of the source of this type of radiation. Make sure you're aware of the hazards and the shielding as well. You could very well see a question or so on the Regents asking you about that. And I've got a picture on my packet here that's not on yours, but it'll kind of give you guys that idea of that. So description / symbol, again, it's a helium nucleus for alpha particles. They are naturally occurring in elements. They have a mass of 4. No external hazard. Internal, though, so if it does get past your skin, like our guest speaker was talking about how smoking causes cancer, it's because there are certain components that are found in cigarettes that once they get into your lungs, they start to undergo alpha decay, and that's the issue. But shielding, skin or paper, so that's what you would need to block it from penetrating and kind of absorbing those particles. All right, beta particles, again, you'll see it most of the time, guys, like this in terms of that electron symbol, but you could see it in terms of where it has the symbol beta. There's no mass. They're dangerous internally and externally, but some cardboard or aluminum foil can shield it. And the source is atomic nucleus of most radioisotopes can give off that beta decay. Positron, radioactive isotopes only. All right, they look like this. They have no mass as well. They're dangerous internally and externally, but again, very similar because these are basically the same thing, except one's the formation of a proton and one's the formation of a neutron. So cardboard and aluminum foil with those. Gamma rays, on the other hand, guys, they are in nearly all nuclear reactions. So whether it's a nuclear power plant or an atomic bomb, this is one of the big dangers of it when things go awry. No mass, all energy. All right, very, very highly penetrating. You need a heavy lead shield or suit, and like we're talking, 6 inches of lead. Concrete, it's something like 2 feet of concrete or so. So one thing, you have this picture in your notes. Guys, this is kind of just showing that if this were to, radioactive material is kind of being given off, okay, that we could actually separate it based on magnets, okay. Positive alpha particles are going to be attracted to the negative plate in a magnetic field, okay. They don't deflect as much as the beta particles, though, because they are heavier, so they don't deflect as much as beta, but they would go toward the negative because they're overall positive. Negative beta particles attract to the positive plate. They're lighter, so they're going to bend more towards the plate. Neutral gamma rays have no charge, so they're going to be undeflected in the electric field, and they go straight through. So just kind of keep that in mind. You could maybe be asked a question about that. Alpha is going to go toward the negative because it's overall positive. So alpha, guys, think positive. Beta, right there, these negative in the symbol. And then if you look at the atomic symbol there, it's negative. And then you've got those gamma rays, which are neutral, so they're going to pass right through. I don't anticipate or think you guys would be asked about positron, but again, just think about it like positive. They would go toward the negative plate. This is the picture that you guys don't have. I put it in after I made copies, but take a look, guys. This is kind of showing you that penetration that it's talking about in your chart up here. This is just kind of a good visual to show, hey, alpha particles can be stopped by your hand because of your skin. Beta particles could go through your skin, but a thin sheet of aluminum would stop them, like a foil hat. Gamma rays can go through both of those. Lead would stop it. Neutrons can penetrate through all that stuff. And then concrete could stop that. So just kind of an idea to show you kind of what it takes, why radiation can be so damaging in terms of like atomic bombs and that type of piece. But remember, nuclear power plants are a little bit different, more controlled than that. So what you guys are going to do now, practice kind of going through these nuclear decay reactions, identify the type of decay, as well as either the part, most of these are, just dealing with that, but be able to kind of go figure out the daughter nuclide from a parent nuclide given the type of decay, or be able to identify the type of decay. There's more practice on this in the binder as well. If you have questions, let me know. I'll see you guys next time.